صباح الخير للجميع. صباح الخير عطوف الدكتور عوني. تسمح لنا نبدأ دكتور؟ الصوت.
صباح الخير.
صباح الورد.
الله يعطيكم العافية.
الله يعافيك. تسمح لنا نبدأ إن شاء الله؟
تفضل، نتشرف.
شكرا. Good morning and good afternoon here and all of the people in different time zone. Good morning and good afternoon. Welcome everybody in this virtual room and the live broadcasting of Jazz, Awaz, and other social medias, as well as the Arabic interpretation via Astrogate YouTube channel of this important seminar. This collaborative seminar on Hayabusa2, the wonderful Japanese mission that brought rock samples from asteroid Ryugu. Before we start, we have some instructions here. For the questions not allowed to ask a question during the talks, and you have two ways to ask your question. You can write your question as a text in the chat panel, or you can use the electronic hand and we'll give you the opportunity to talk. Something else, please switch off your mic and camera except the speakers, especially during the welcome speech of His Excellency, the Japanese ambassador in Jordan, Mr. Shimazaki Koru, and Dr. Yoshikawa Makoto talk. During that, please switch off your mic and camera. Hayabusa2, the Japanese mission that brought rock samples from asteroid Ryugu. It's amazing mission. This event organized by JAXA, the Japanese Aerospace Exploration Agency, and the Jordanian Astronomical Society, JAZ, the Arab Union for Astronomy and Space Sciences, AWAS, and the Embassy of Japan in Jordan. And we have also Arabic interpretation in Astrogate YouTube channel. Welcome speech. We'd like to invite right now Dr. Auni Al-Khassani. He's the president of Jordanian Astronomical Society, Major General retired, and he's the General Director of the Regional Center of Space Sciences. Please welcome, sir.
Good morning, everybody. Your Excellency, Mr. Kaoru Shimazaki, the Ambassador of Japan in Jordan, Professor Dr. Makoto Yoshikawa, Mission Manager, Hayabusa2 Project Team, representative of the Japan Aerospace Exploration Agency, JAXA, distinguished experts and guests, ladies and gentlemen. Good morning from Jordan and good evening from Japan to all of you. It's my great pleasure and honor to participate with you today in this scientific seminar, which is entitled Hayabusa2, the Japanese mission that brought rock samples from asteroids. This comes as a collaboration between the embassy of Japan in Jordan, the Japan Aerospace Exploration Agency JAXA, the Jordanian Astronomical Society JAS, and the Arab Union for Astronomy and Space Sciences AWAS. In fact, the Jordanian Astronomical Society is a voluntary organization that was established in Amman in 1987 with the following objectives: gathering astronomers, particularly emitters, in Jordan and the Arab world as a whole, in order to develop their astronomical knowledge and skills through the exchange of information, research, and observational experience. In order to achieve this goal, JAS has tried to make available all what emitters, astronomers need in this regard, such as binoculars, telescopes, books, magazines, and so forth. In addition, the activities of JAS focused in the beginning of the weekly lectures that are delivered every Thursday evening at the JAS Cultural Forum, which was delivered every Thursday evening at the JAS Cultural Forum, which was formerly at the Haya Cultural Center from 1990 to 2010, and later at the Arab Union for Astronomy and Space Science. In fact, the JAS weekly meeting vary in form from the scientific lectures from the general audience to documentaries and science fiction films, and from astronomical competitions to hosting gifted students and competition to hosting a gifted student and youth who have achieved some distinguished works. The Jordanian Astronomical Society has been interested in the subject of astronomical observation since its start. For the reasons JAS organizers star nights, and for this reason, the JAS organizes star nights and observing camps for its members and the public whenever there is any significant astronomical events, such as lunar and solar eclipses, planetary transits, meteor showers, comets, planetary opposition, and so forth. In this regards, in the late 1990s, JAS has established the Hamza Astronomical Ecological Camps in Azraq area in the Eastern Badia, which is located at around 150 kilometers from Amman, where we have organized more than 300 observational camps for the youth during the past 20 years. And we aim to further develop the Hamza camp or to establish new camps in order to develop astronomy tourism in Jordan. In fact, JAS has been involved in spreading awareness in astronomy and space science among its school students by organizing star nights, lecture, and training courses for students and teachers. And more recently, we have been involved in training teachers dealing with Syrian refugees. Unfortunately, most of such observational activities were stopped lately due to the lack of proper instruments at JAS, such as binoculars, telescopes, and CCDs. On the other hand, the Jordanian Astronomical Society has also played an important role of the professional and institution levels. For example, the establishment of the Institute of Astronomy and Space Science at Al-Bayt University in the city of Mafraq came as a response to a recommendation made by the Society at the first Arab Astronomical Conference held at the University of Jordan in 1992. In 1998, JAS was a key player in establishing the Arab Union for Astronomy and Space Science based on Amman, which has been playing an important role in developing astronomy and space sciences at the Arab level In this regard, 12 conferences on astronomy and space science were organized in collaboration between JAS and EWAS. Our event today in collaboration with the Embassy of Japan in Jordan and the Japanese Space Agency JAXA is another example of the collaboration between our both countries, Japan and Jordan. I would like hereby to extend my great gratitude to the people of government of Japan for the continued support of Jordan and its local communities in the fields of development and capacity building. In fact, this event comes as another step along a process that the Jordanian Astronomical Society has started more than 33 years ago. We would like to hereby to emphasize the importance of space exploration in the comprehension of our universe and our place in it, and to utilize space exploration as a way to encourage the youth into the varied specialties of science, technology, engineering, and mathematics, which are essential for the sustainable development of our economy. Your Excellency, Ambassador of Japan in Jordan, based on what I have just mentioned concerning the role played by the Jordanian Astronomical Society in developing science for the local community in Jordan, we look forward we look forward that to receive any assistance from Japan in the form of telescopes and other instrumentation in order to sustain the impetus of our activities and continue the educational and cultural roles played by our organization. Once again, I would like to welcome you in this important event and thank you for your participation. And I hope that this will be the start of fruitful collaboration between the Jordanian Astronomical Society and the Arab Union for Astronomy and Space Science on the one hand, and the Embassy of Japan in Jordan and the Japan Aerospace Exploration Agency, JAXA, on the other hand. Again, I would like to welcome you on behalf of JAS and EWAS and say you are welcome, and we are very much eager to start cooperation between our two organizations. And thank you very much, and my best regards to all. Thank you.
Thank you. Thank you, sir. Now, welcome speech of the Japanese ambassador in Jordan, His Excellency Mr. Shikazaki Karu. Please, sir, welcome. You are most welcome. Please, welcome.
Distinguished guests, viewers, ladies and gentlemen, good morning, the people and friends in Jordan, and good evening to those in Japan. It is my great pleasure and honor to greet you at today's event, co-hosted by Jordanian Astronomical Society, Arab Union for Astronomy and Space Science, and the Embassy of Japan to the Hashemite Kingdom of Jordan. First of all, I'd like to express my sincere appreciation for the great efforts made by Dr. Amar Sakaji, the Vice President of Jordanian Astronomical Society, and proposer of today's online seminar. Thanks to Dr. Sakaji's efforts, we introduced the bold challenge and great success of Hayabusa2 Project team to Jordanian friends, with participation of a distinguished guest from JAXA, Japan Aerospace Exploration Agency. As a core performance agency to support the Japanese government's overall aerospace development and utilization, JAXA has been conducting integrated operations from basic research and development to utilization. One of the recent achievements of JAXA was the Hayabusa2 project, led by a world-famous astronomer, widely acknowledged as a great asteroid hunter. Yes, he's today's first panelist, Dr. YOSHIKAWA Makoto. I'd like to express my sincere gratitude to Dr. Yoshikawa, Mission Manager of Hayabusa2 Project team, for attending the event despite an extremely busy schedule. Dr. Yoshikawa was nominated in Nature's 10 as a world-leading astronomer. Being involved in a series of uncrewed space exploration operations under the JAXA, he has greatly contributed to the recent development of astronomy. I believe that his presentation can stimulate the curiosity of Jordanian and Arab astronomers today. It is also my great pleasure to have other distinguished and leading scholars in the field of astronomy, namely Dr. Amaru Sakaji, Dr. Hannah Sabat, and Mr. Adri Hanabi. Despite the friendly relations between Japan and Jordan, either at the level of government or people, unfortunately, academic seminars with participation of both Japanese and Jordanian scholars have been rarely held. Therefore, I'd say this seminar is really a unique opportunity. The relationship between the two countries is now in the astronomical level. Ladies and gentlemen, we are facing an exceptional challenge caused by the COVID-19 pandemic, both in Japan and Jordan. However, we can turn challenges and difficulties into positive opportunities. The most recent and symbolic example of which is, I would say, this online seminar today. Our adaptation to the new environment made active academic interactions between Japan and Jordan possible in virtual way. And it proves that our strong ties and interactions are never stopped under any circumstances. I hope the seminar can be a trigger of further development exchanges between Japan and Jordan, and possibly more broadly the Arab world. I'd like to conclude my remarks by affirming that the Embassy of Japan will continue to do its best to strengthen our ties in different levels, including academic ones. Thank you very much for your kind attention. شكرا جزيلا. どうもご清聴ありがとうございました。
Thank you. Thank you.
Thank you so much, Your Excellency, Mr. Shimazaki, the Japanese ambassador in Jordan. Thank you so much. Right now we come to Dr. Yoshikawa, the amazing astronomer and professor of theoretical physics. He's one of the top 10 as according to Nature scale, top 10 researcher worldwide. He's the mission manager, and he will talk about challenging mission of Hayabusa2. Please, sir, welcome.
Thank you very much. I'm very happy to be here. And at first, I thank you very much for inviting me this science seminar. So today, I'm going to talk about the Hayabusa2 in detail. So at first, I show you this model. Can you see this? This is a very precise asteroid Ryugu model. So Hayabusa2 studied this asteroid quite in detail. So today, I'm going to talk about the Hayabusa2 mission and also about this small asteroid Ryugu. Okay, so now I share my computer screen. Okay, so the title is Asteroid Sample Mission Hayabusa2. I am mission manager of Hayabusa2. Okay, at first, I show this slide. This is a map of world and Japan. And in this world map, I think Jordan is here and Japan is here. So very long distance from Jordan to Japan. I think the time difference is 7 hours. So now you are in the morning, but me, I am in the evening. And JAXA has several offices in the world like this. And also, we have many offices and facilities inside Japan. So in Tokyo, we have Tokyo office. And also, headquarters is near Tokyo office. And I am working here, this one, Sagamihara campus. So in this campus, we made Hayabusa2 spacecraft, and we are operating Hayabusa2 from here. Okay, so this is a JAXA, and next slide is the Japan's planetary missions. Actually, Japan, we launched a lot of artificial satellites around the Earth, but planetary missions, the number is not so much like NASA, but we had many experience of planetary missions. So first one were Sakigake and Suisei. They were first planetary mission of Japan. They were launched 1985, and the target object was a comet Halley. And then we launched Hiten. Hiten went to moon, and we made a lot of swing-by experiment using moon. And then we launched Nozomi, which was Mars Explorer, but this was inferior. We could not orbit Nozomi around the Mars. And then we launched Hayabusa. This is the Asteroid mission, Asteroid sampling mission, and Hayabusa had a lot of troubles, but it was able to bring back the sample of Itokawa. And then Kaguya, this is a moon mission. This was quite successful. And then we have Akatsuki mission. This is a Venus mission. Akatsuki also had trouble, but later it was able to orbit around the Venus, and now we had lots of data from Venus. And also Icarus was launched with Akatsuki, and this is a world first solar cell mission, and this was successful. And then 2014, we launched Hayabusa2 with small spacecraft program. So today, I will talk Hayabusa2 in detail. And finally, we launched Baby Colombo. Actually, this is a collaboration with ESA, Europe, and now we are operating MEO spacecraft. Okay, so this is Japan's planetary missions. So the number is not so much, but we had several very challenging missions, like Hayabusa 2. I quickly asteroids. So this shows the planets and dwarf planets. Of course, you know this quite well. In our solar system, we have 8 planets. In Japan, children remember these 8 planets like Suikin, Chikamok, Dotenkai. This is a Japanese word. Anyway, there are 8 planets, and now there are 5 dwarf planets. Pluto was originally classified as planet, but now it is a dwarf planet. And the Ceres, this is the first asteroid discovered. Ceres is also a dwarf planet, and Eris and Haumea and Makemake, these 5 are dwarf planets, so smaller than the planets. And today's topic is asteroids. Asteroids are much smaller than dwarf planet. And do you know how many asteroids now we have discovered? This one. Now we know more than 1 million asteroids. Too many. And recently, every year, lots of asteroids were discovered because now planetary defense activity is very active. Planetary defense means we search asteroids that collide to the Earth. So we call such asteroid near-Earth asteroid. So in this figure, the center is the Sun, and the blue lines are orbital planets: Mercury, Venus, Earth, Mars, and Jupiter. And these gray dots are asteroids. So there are lots of asteroids between the Mars and Jupiter orbit. This gray zone is the asteroid belt. And these red dots are also asteroids. This red one is a near-Earth asteroid. So as you can see, there are lots of red dots near the orbit of Earth. So now many people are searching such near-Earth asteroid. So the number of discovered asteroids is rapidly increasing. And also, many spacecraft explored asteroids. So I show you the photo taken by spacecraft. So here, this is a series, the first asteroid discovered. So this is a spherical shape, and also Vesta is also has a spherical shape. But you can see all the other asteroids have irregular shape. This is a feature of asteroid, okay? Because the self-gravity is very small, so the shape cannot be spherical except those big ones. However, when Hayabusa2 approached to Ryugu, it took this picture, the left-handed picture, this one. So Ryugu, this is very small asteroid. The diameter is just 1,000 meters, just 1 kilometer. But the shape is not irregular. The shape is spinning top shape. And then a few months later, the OSIRIS-REx spacecraft arrived at Bennu asteroid. The shape is quite similar. This is very interesting. Bennu, the diameter is just 500 meters, very small, but the shape is not irregular, but spinning top. So now we know that even if the asteroid is very small, sometimes the shape is not irregular. And finally, this asteroid, Alcos, this is very interesting. This is a trans-Neptunian object. So this orbit is far from the Pluto. And this photo was taken by New Horizons spacecraft. Anyway, like this, I think there are many unknown shaped asteroids in the solar system. And I show you the orbit of Ryugu. I draw this figure today. So the position of Ryugu is today's position. So in the left-hand figure, you can see asteroid belt clearly. This black region is asteroid belt. And Ryugu's orbit is inside of asteroid belt. So please look at the right figure. So this is Ryugu, today's position, and this is the Earth. So actually now, Ryugu is not far from the Earth. And the orbit is just between the Earth orbit and the Mars orbit. And the spacecraft Hayabusa2 went this asteroid. And I summarize the importance of small solar system bodies. Small solar system bodies means asteroids and comets. We think asteroids and comets are very important because if we study such small bodies, we can know the origin and evolution of the solar system. And also maybe we can have some clues to the origin of life on the Earth. And also they are important because of the planetary defense or space guard. If asteroids collide to the Earth, we will have very large damage. So we want to avoid such collision. And also, these small bodies are important in terms of resource. This image is the asteroid Ryugu, and its composition is a rock. But maybe in some place, there is an asteroid whose composition is metal. So we can use such asteroid as a resource. And some asteroids, like Ryugu, has a water. So we can use water from such a small body. And manned mission. This is also important. So more than 50 years ago, astronaut went to the moon. And now we are discussing to go to the Mars. But Mars is very far for human mission. So before going to Mars, people try to go to asteroids much closer than Mars. So in that case, the asteroid is a good target for manned mission. So like this, small bodies like asteroids or comets are very important for human beings. Okay, so let's move on to the Hayabusa and Hayabusa2 as the sample return mission. First, I show you the history of Japan's asteroid explorations. The starting point was 1985. This is a cover of proceedings that we had in 1985. At this meeting, we discussed sample return from asteroid. And then we had Hayabusa mission from 2003 to 2010. This is a Hayabusa spacecraft, and the background, this is Itokawa, asteroid Itokawa. And Itokawa is S-type asteroid. And Hayabusa had a lot of technical troubles, but we were able to get the surface material of Itokawa. And then we had Hayabusa2 mission, which was launched to 2014. The target asteroid Ryugu, and this is a C-type asteroid. And I will talk about this in detail later. And now in JAXA, we are discussing the future missions. And one of the candidates was the Trojan asteroid. The Trojan asteroid is orbit near the Jupiter. And we discussed to use the solar sail spacecraft. However, this proposal was not accepted yet. And now in JAXA, we are discussing MMX mission. And this is a sample return mission from Phobos. Phobos is the satellite of Mars. So now this MMX mission is ongoing, and many people in JAXA are working for this MMX. Okay, so this is a quick history of Japan's asteroid exploration. And maybe it's better to explain the name of Hayabusa and Hayabusa2. And Hayabusa2, Hayabusa, this is a Japanese word, and it means falcon. Falcon is this bird. And in Japanese language, we write like this. Okay, so the meaning of Hayabusa is falcon. And Itokawa, this name comes from the person. This is Professor Hideo Itokawa. He is the father of modern Japanese rocketry. In this photo, he had small rocket. This is a pencil rocket. This is the first rocket of Japan. And Ryugu, this name comes from a story, Japanese famous story called Urashima Taro. Ryugu is the name of undersea palace. Okay, so all of these are Japanese, but they have these meanings. And anyway, Hayabusa and Hayabusa2 is sample return mission. So we must develop new technology for sample return. This slide summarizes the important technology to do the asteroid sample return mission. So for Hayabusa, we developed ion engine, autonomous navigation, sample collection system, and reentry capsule. So these are very basic technology for sample return. And for Hayabusa2, we developed another technologies such as impactor system and K-band communication system. I will show impactor system later. And maybe next mission, for example, Torian mission, then I think there are many, we need many new technologies. And this slide summarizes the science of asteroid sample return mission. So this is a Itokawa Hayabusa spacecraft explored, and this is a Ryugu Hayabusa2 visited, and this is Earth. So all of these bodies were formed about 4.6 billion years ago. At that time, there was the molecular cloud, and molecular cloud shrinked, and in the center of molecular cloud, the sun was born. And then in the disk around the sun, these planets or asteroids were born. But the planet like Earth, it was very big. So when Earth was born, the temperature increased and all of the material melted. So if we study the material in the Earth, we couldn't know the original material. However, Itokawa or Ryugu, such asteroids maybe were not melted at the beginning. So if we get the samples from these asteroids, we can know the original materials. And Ryugu is a C-type asteroid, which means it may have the organic matters. So organic matter is very important for the life of the Earth. So we want to study organic matter from the sample of Ryugu. And here I have a very detailed chart. This shows the history of asteroid. The left-hand side, this is a molecular cloud, more than 4.6 billion years ago. And then here, this is the asteroid. So we know asteroid quite well. We have lots of data. And molecular cloud, yes, we know molecular cloud from the astronomy. But we don't know between this. At first, protoplanetary disk was formed, and then the planetesimal were formed. And then the parent body of asteroids were formed, and asteroid. So maybe this scenario is correct, but we don't know the detailed things. So we call this region missing zone. So Hayabusa 1 and 2 will solve this missing zone. And the most interesting thing is the organic matter, I think. And Hayabusa2, now we have the material of Ryugu by Hayabusa2. So still, sample analysis is not started, but soon it will start. And then if we find amino acid in the sample, maybe we can get some clues for the origin of life on the Earth. As you may know, amino acid has two structures called left-hand structure, L-chiral, and right-hand structure, D-chiral. And most life on Earth use left-handed amino acid. Why? We don't know this. So if we can find the amino acid in the sample of Ryugu, we will check its structure, and then we can study about the origin of solar system, of life on the Earth. So I think this is a very important part of the Hayabusa2 mission. Okay, so now I move on to Hayabusa2. First outline. So I already talked about this. Hayabusa2 is a second astronomical mission following Hayabusa, and target asteroid Ryugu, C-type near-Earth asteroid. C-type is important because it has the organic matter. So, okay, and also we have engineering objective. Engineering objective is to develop technology that perform round-trip mission reliably. As I said before, Hayabusa spacecraft had a lot of troubles. So we modified spacecraft for Hayabusa2. And Hayabusa2 does not have serious trouble. So our technology has developed. And this is Hayabusa2 spacecraft. This is not so large. The total mass, including fuel, is just 609 kilograms. And the body size is just 1 meter by 1.6 meter by 1.25 meters. So it is not so big. And the shape is quite similar with the Hayabusa 1, original Hayabusa. But we modified a lot of parts inside the spacecraft. And it has 4 science instruments. I will show this later. And it has 1 lander, Mascot, which was made by DLR, CNES, German and France, and 3 small rovers, Minerva 2. I will show you how they work in Asteroid. And yes, this one is a science instrument. So I will talk about this later. And the most important payload for the spacecraft is this one, ion engine. And I quickly explain the ion engine. So ion engine, the fuel is xenon, and xenon is ionized by microwave discharge. So here, plasma, this means ion of xenon. And ionized xenon is accelerated by high voltage here. And actually, the thrust level, the strength is not so big, very small. But we use ion engine for a long time. So gradually, the orbit of spacecraft is changed. And the good thing is the energy source. Energy source is the sun. Ion engine is working by electricity, and electricity was made by solar paddle using the sunlight. This slide shows the science instruments. There are 4. The first one is optical navigation camera, ONC. We have 2 kinds of ONC. One is a telescopic one, and the other one is wide-angle camera. Actually, we have 2 wide-angle cameras. And second one is a LiDAR, light detection and ranging. This LiDAR is used to measure the distance between the asteroid and spacecraft. And third one, this is a NIRS 3, a near-infrared spectrometer. We use this to study the composition of the surface material of Ryugu. And finally, this is a TIR, thermal infrared imager. Using this, we can measure the temperature of the surface of Ryugu. So these are science instruments. And we have 12 deployable robots. The upper left, this is a reentry capsule. I will talk about this in detail in the rate of this talk. And the middle one, this is the deployable camera. I will also explain how we use this. And this is a Mascot lander. And there are 3 Minerva-2, Minerva-2-1. There are 2 Minerva-2-1 and 1 Minerva-2-2. And this one, this is a small canyon impactor to make the small crater on the surface of Ryugu. And these were target markers. These are artificial landmark. These are used before spacecraft touchdown. Also, I will show you how we use this. And the Mascot lander was made by Germany and France, and it has 4 instruments. Camera, micro-omega is a spectral scope, and a radiometer, and a magnetometer. And this Mascot can move like this. Actually, it moved once or twice. And these Minerva-2 also can hop like this. And so they can move on the surface of Ryugu like this. So using these instruments, we can do very wide scale range science. This chart shows the distance scale. +3, this is a logarithmic scale, so +3 is 1 kilometer, and 0 is 1 meter, -3, 1 millimeter, -6, 1 micrometer. So these are payloads of Hayabusa2. So using these payloads, we can study Ryugu from macro scale to micro scale. So we can do lots of science. Okay, so up to here is the explanation about the spacecraft. So now I talk about the operation. At first, I show you the launch of Hayabusa2. It was 3rd December 2014.
Flight mode on.
This is the Panelist Space Center in Japan. This is HTA rocket.
Summer batteries
So
activation.
now countdown.
All systems are ready. Main energy ignition. SRB ignition and liftoff.
小惑星探査機はやぶさ2と小型副ペイロード3機を搭載した H2A ロケット26号機は平成26年12月3日午後1時22分04秒に種子島
Yes, this was very beautiful launch, and the orbit was perfect. And then this is the orbit towards to Ryugu. So this is the sun, and this blue line is Earth's orbit, and this green line is the Ryugu orbit. This is a schematic figure. So launch is here, and at first, spacecraft orbited around the sun, along the orbit of the Earth, like this. And just 1 year later, a spacecraft approached to the Earth and performed Earth swingback. And then orbit was changed largely, and then spacecraft orbited around the sun twice, like this, once and twice, and arrived at Ryugu. So this is a trajectory to Ryugu. And these orange line means the ion engine operation. Now I'll show you computer graphics image for this orbit. This one. So yes. So this is from launch to the asteroid arrival. At first, spacecraft left from the Earth like this. Yes, this is the ion engine. So sometimes spacecraft use ion engine. This white line means ion engine operation. Then it came back to the Earth to perform Earth standby like this. And spacecraft changed its orbit by using Earth gravity. And using ion engine, the orbit of spacecraft changed little by little. So white line indicates the ion engine operation. And one more revolution, Hayabusa2 arrived at Ryugu. Yes, so this is arrival. So after this, we did a lot of operations. This is a summary of Hayabusa2 operation at the asteroid. Okay, launch and everything by. Then Ryugu arrival was June 27th, 2018. So after this, at first we observed Ryugu in detail, and then we separate two small rovers, Minerva 2-1, and then we separated a Mascot lander, and the first touchdown was done in February 22nd, 2019. And then we did the impactor experiment to make the artificial crater on the surface of Ryugu. And second touchdown was done in July 2019. So up to here, all the operation we planned were finished. And this is an additional experiment. Target marker, the artificial landmark, was left. So we use two of them to make the artificial satellite around the Ryugu. And also another small rover, Minerva 2-2, we made this also a satellite around the Ryugu. So in total, 3 small objects were orbiting around Ryugu as a small satellite. And Hayabusa2 left Ryugu in November 2019, and just 1 year later, it came back to the Earth. This is December of last year. So maybe it is better to show what we did in Ryugu by computer graphics movie. So now I show you this movie. So it starts from the arrival at Ryugu. Yes, this is Ryugu arrival. Then next, I show the Minerva 2-1 separation. The altitude is about 55 meters, and these two small rovers were separated very slowly, and they went down to the surface of Ryugu like this, and bounced several times and stopped. And then it can hop like this. And by hopping, they can move the position, and they took photos and measured the temperature. Both of two are successful. And then next is Mascot Separation, also about 50 meters in altitude. And Mascot was landed successfully like this, and it could took lots of data on the surface of Ryugu. And next was touchdown. But since the surface of Ryugu was very rough, so actually we postponed the touchdown. But we separate only target marker. This is a target marker, the artificial landmark. The size is about 10 centimeters. So we put this on the surface. Actually, it locates near the touchdown point. And the spacecraft has the flash lamp. So target marker was illuminated by the flash lamp. And the spacecraft camera can watch this target marker, and it can know the position. Okay, so the actual touchdown was done in February 2019. So spacecraft went down to the surface. The altitude is about 8.5 meters, and it found target marker. And looking at the target marker, the spacecraft moved very precisely. And this red line is a laser light to measure the distance. And finally, it made a free fall. Actually, the speed is very slow. This movie shows very fast. And sampler horn touch the surface, and the small projectile was shot like this, and the fragments went up. Like this, we can get the surface material. So first touchdown was successful. I will show you the real image later. And next challenge is the impactor. We try to make the small crater on the surface of Ryugu. So spacecraft went down to the asteroid about 100 meters and separate this impactor. And the spacecraft quickly moved because impactor will explode 40 minutes later. So spacecraft must hide behind the asteroid to avoid the fragments from the impactor. But if spacecraft hide, we couldn't see the impact experiment. So we separate this small camera. This is a deployable camera, DCAM-3, and this small camera could observe the impact experiment like this. Yes, this is a DCAM and explosion and ejector from the surface of Ryugu. So separate DCAM deployable camera was able to image the ejector. I will show you the real image later. Okay, so this impact experiment was also successful, and we were able to make the actual crater. The size of crater was about 15 meters in diameter. And finally, we will try to do the second touchdown near the crater. So I stopped. So this is a artificial crater, and actually inside the crater is rather dangerous. So spacecraft touchdown near the crater, about 20 meters from the crater. And this area also, this area was covered by the ejector of crater. The purpose of second touchdown is to get the subsurface material. So if spacecraft touchdown this area, we can get the subsurface material too. And touchdown method is similar as the first one. So about from the 8.5 meters, spacecraft went down like this, and the sampler horn touched the surface, and projectile was shut, and fragments went up. Okay, so second touchdown was also successful. So up to here, all the mission was okay, but as I said before, we tried another experiment, that is an artificial satellite experiment. Since we have 3 target markers, so we use 2 to make the actual satellite. So this is a target marker separation. This is target marker 1, and then change the direction, and second target marker were separated like this. So at this time, 2 small bodies were orbiting around the Ryugu, and we observed its motion from the spacecraft. Yes, one is here. This is an equatorial orbit, and the other one is here. This is a polar orbit. So such experiment, all of these experiments was successful. Okay, then I show you real image that we take near the Ryugu. So at first, I show you this image. This is the first image of Ryugu, which was taken by the spacecraft. At this time, this is just a point. We cannot see the shape. This was February 2018, about 4 months before the arrival. Okay, so next is approaching Ryugu. Now you can see the shape of Ryugu. Still, it is a point, but then you can see the shape like this. This is the approaching phase. And the shape was something like this. And when we saw this image, we were very surprised because we never imagined such shape. Okay, so this is a group photo of Ryugu arrival, June 27th, 2018. We were very happy. And actually, I am here. This is me. And this is a project manager, Professor Tsuda. And this is a real photo of Ryugu. So the shape is spinning top. We have never imagined this shape. We are very surprised to see this. And also, we are surprised to see the surface. The surface of Ryugu was covered lots of boulders, lots of rocks like this. There are no wide flat areas. So this makes touchdown very difficult. So actually, we postponed touchdown about 4 months. And then we continued to observe Ryugu, and we had lots of scientific data. This is a precise shape model that I showed you at the beginning of this talk. And this is a color image. The Ryugu is very black. This means that the surface material of Ryugu contains lots of carbon. And this one, this is a temperature measurement by thermal infrared imager. And bottom right, this is a gravity of Ryugu. And the upper right, this graph is very important. The data of Ryugu is this black curve. And this is a spectrum of near-infrared. And you can see here a very small absorption. This absorption means that the surface material contains water. So this is very important data. And surface of Ryugu is something like this. This photo was taken by the Minerva 2-1 small rovers. You can see the surface is quite very rough. This white light, this is the sun. So right movie, you can see the motion of the sun seen from the surface of Ryugu. So these are the photo by Minerva 2, and these are photo by Mascot. So left-hand side movie, you can see Mascot is dropping down. This is Mascot. And the middle image and the right image, they were taken by Mascot. It took very precise image of the surface rock of Ryugu. And the very difficult thing was touchdown. This shows the touchdown site selection. Upper left, this is a whole surface of Ryugu. And at first, we select this area, L08, because this area seems to have less boulders. However, this L08 area had lots of boulders like this. So we chose this small area. The diameter is 20 meters. In this area, the rocks, the big rock is less than other area. So we dropped the target marker. We try to drop the target marker inside this 20-meter area, but the target marker dropped 5 meters outside from this circle. So we studied around this area, and we found two possibilities. One is this red region, 12 meters region. The other one is this 6-meter region, very near to the target marker. And finally, we chose this 6-meter region for the touchdown. Before going to touchdown, I show the target marker release. This small dot is target marker, and this red circle is a 20-meter diameter area, and this is a shadow of spacecraft. Okay, so now this is a movie, so I start this movie. So target marker is dropping, and the spacecraft was watching the target marker, and it is spacecraft controlled its position by itself. So we call this target marker tracking. So target marker tracking was successful. But at this time, we did not do the touchdown. So touchdown was done after 4 months later. This is the first touchdown. The target marker is here, and this is the touchdown area. And this is a movie of touchdown. You can see the sampler horn here, and it will soon touch the surface. Like this. Yes, touchdown. And soon the spacecraft went up. So you can see lots of stones blown up. And actually, this movie is 5 times faster than real. So actual speed is very slow. And the touchdown accuracy was just 1 meter. The error of touchdown point is just 1 meter. So we think the accuracy is quite nice. And we know where sampler horn touches this area. Okay, so this operation was very difficult, but it was successful. So now this is a group photo of our operation room. There were lots of people like this. And next challenge was the impact experiment to make the artificial crater. So I already talked about this. Spacecraft separate impactor here, and impactor explode around here. But before the explosion, spacecraft must hide behind the asteroid to avoid the fragments from the impactor. But before that, we separated DCAM3 here, and this camera can watch this impact experiment. So now I show you real image. So this is a separation of impactor, like this. And then after explosion of this, you can see the ejector from the surface of Ryugu, like this. I have a video too, movie too. So you can see how the crater grows up. So this impact experiment was also successful. And later, spacecraft went to this impact crater, and the image is like this. The left one is before impact, the middle one is after impact, and right one is comparison. So you can see clearly that we were able to make a crater like this, and this size is about 15 meters. So the purpose to make actual crater is to get the subsurface material. However, the inside crater is very dangerous, so we studied around the crater, and this is a result. And we found in these black-colored region, subsurface material were accumulated. So we chose here for the second touchdown. And yes, please look at the left image. So this is the impact crater, and this yellow circle is the place of second touchdown. The distance is about 20 meters. But as you can see, there were lots of big rocks around this area. So we studied this area in detail, and we made a lot of simulation. And finally, we tried touchdown here. Since the first touchdown was successful, if we did the second one and it became failure, it is not good. So before doing the second touchdown, we studied a lot around here, and also we made a lot of simulation for touchdown. And touchdown method is similar. So I skip this, and I show you the movie of second touchdown. And this time, this movie is 10 times faster than real, so it is very fast. Like this. So again, you can see a lot of stones blown up. Okay, and the second touchdown was also successful, and the touchdown accuracy was better than first one. The error was just 60 centimeters. And finally, we did the artificial satellite experiment. Can you see small white dot in this right figure? This is a movie actually, and we can observe target markers, and Hayabusa2 were orbiting around the Ryugu. Okay, so this is a farewell Ryugu. This is the last image that we took at the Ryugu. Spacecraft left Ryugu November 13, 2019. So the Ryugu becomes smaller and smaller. Okay, so let's move on to the final part, return to the Earth. This is a trajectory to the Earth. The trajectory is simple. Here, a spacecraft left Ryugu, and it moved like this red curve, and came back to the Earth. So just one revolution around the sun. And we use IO engine twice, this part and this part. And this final part, reentry terminal guidance, this is very important. So I show you this in detail, this one. So this is a trajectory of spacecraft, and we made a TCM. A TCM means trajectory correction maneuver. And these TCM must be very precise. We have 5 TCMs. For these TCMs, we used chemical thrusters. And I wrote here the velocity change. First one is 50 centimeters per second, and second one is just 1 centimeter per second. And TCM3, this is very important. After TCM3, the trajectory of spacecraft changes. That goes to the Woomera Desert in Australia. And we have small correction, TCM4, and then a capsule was released. And after capsule separation, TCM5, this is important because if we do not do this TCM5, spacecraft also collide to the Earth. So by TCM5, the spacecraft avoid to colliding the Earth. So now I show you another computer graphics movie. This is Hayabusa2 Earth Return. Okay, so this is Earth and Hayabusa2 orbit. So first, TCM1. Yes, this is a spacecraft, and you can see a small jet. Now, yes, very small jet, small correction of orbit. And then this is a TCM3. This is also not so large jet, but orbit can change like this. And then this is a reentry capsule separation. The spacecraft changed its attitude like this, and the capsule was separated like this. This is about 12 hours before the reentry. And spacecraft changed its attitude again, and this is TCM5. This is to avoid the Earth collision. Okay. And from the spacecraft, the capsule was seen like this. So we tried to image the capsule from the spacecraft because capsule became fireable when it entered the atmosphere, like this. Yes, so surface of capsule became about 3,000 degrees in temperature. So we tried to image from spacecraft, but actually we cannot image the capsule from spacecraft. And spacecraft went away from the Earth. And from the ground, we were able to see fireball clearly. I will show you the real image later. And at the altitude of 10 kilometers, parachute deployed. And then the capsule went down slowly like this. And we found the capsule early morning on December 6th last year. Okay, so this is a capsule reentry. Yes, so this is again the reentry flight sequence. So after separation, capsule became fireable, and then at the altitude of 10 kilometers, heat shield separation, a parachute opening, and a beacon transmission started. So using this beacon, we were able to find the landing place of capsule. However, we have several methods to search the capsule. The first one is optical observation from ground and aircraft. And the second one, this is very important. Using beacon, we can detect the place of capsule landing. And we had marine radar too. Marine radar can detect the parachute. And we have helicopter, of course, and a drone. So by using this method, we wanted to find a capsule as soon as it landed. So these are a photo. The upper left, this is a marine radar, and the upper right, this is a drone. And lower left, this is a beacon antenna, and the middle is a camera and a helicopter. And this is Woomera, Australia Umera area. So in this area, we must land the capsule. And actually, the first Hayabusa, original Hayabusa, also the capsule landed in this Umera area. So Umera area is like this, and no people is living, so it is very safe place for landing of capsule. And from JAXA, about 70 people went to Umera to get the capsule. And they sent me lots of photos like this. This is not important one, but these photos, many birds and animals. And actually, this is a
並走してる。遅いぞ。もっとスピード上げて。
and this is a very nice landscape. And you can see the weather seems very nice. However, sometimes weather became bad. If weather is good, the night sky is very beautiful, like this. But the day before the capsule reentry, it was raining. So we were very nervous about the weather, but the reentry day, the weather was very nice. And this is an image of a capsule fireball. In the left image, you can see the trace of a capsule like this. And the right-hand photo, this is very beautiful. This is a capsule trace. And this one, this is another satellite around the Earth. I think this is a Southern Cross. So now I have a movie. Yes. So this is a capsule moving in the night sky. So everything goes well. And we were able to find this day. And this is a photo when we found the capsule. This is a parachute, and this is a capsule. And we collect this capsule. So now I talk about this sample of Ryugu. At first, I explained the structure of reentry capsule. This is a reentry capsule, and it has two heat shields, front one and rear one. And inside the capsule, this green part, this is important. This is a sample container, and inside this, we have the sample of Ryugu. So this figure shows the structure of sample container. So in the sample container, there is another box. This is sample catcher. And sample catcher has 3 chambers, ABC. So in these chambers, Ryugu sample is stored. Okay, so the real photo is this one. This is a front heat shield. This is a back heat shield. And left, bottom left, this is an instrument module. And inside this equipment was located. And inside this, this sample container. And at first, we brought this sample container in the quick look facility in Umera, and we took gas from the inside. And we analyzed the gas, and we found the gas was emitted from the sample of Ryugu. And then capsule was quickly brought to Japan and JAXA, and this photo is in JAXA. At first we prepared to open this sample container. This equipment is very complicated, and anyway, we put this container to this equipment. Actually, this is a clean chamber like this. So inside this chamber, we opened the capsule. So we opened the container. So now I show you a sample of Ryugu, this one. You can see very black grains here. This is chamber A. So this is for the first touchdown. So we were able to get lots of samples from Ryugu. The total amount of sample was 5.4 grams. So I show you all the samples. So at first, in this sample container, we found small grains like this. And chamber A is this one. And chamber C is this one. So grains in chamber C is much larger than chamber A. Chamber C is a sample of second touchdown. So now the people of curation were working for these samples, and they took samples from the container, and now they are examining these samples like this. And but analysis was not done. It will start in June of this year. When I saw this sample, I remember the case of Hayabusa. This is a case of Hayabusa, quite similar. And this is a sample container. And when opened this, we couldn't see any samples. But here we found many small grains. And this is a grain from Itokawa, but very small amount. So now, in this time, we have lots of samples. So I think we can do a good sample analysis work. Okay, so this is a schedule. So now we were doing this phase 1 work. So after this phase 1 curation work, initial analysis will start from June of this year. This initial analysis will be done by the members of Hayabusa2 project. And then I think from the June of next year, the sample will be distributed to worldwide. Okay, so that's all, but finally I talk another thing, extended mission. And these images of the Earth were taken by the optical navigation camera when spacecraft go away from the Earth. So after this, we continued operation of spacecraft. That is extended mission. So the spacecraft is still healthy, operational, and 50% of xenon was still remained. So we chose one very small asteroid, 1998 KY26, for the next target. But there's one problem. It took about 10 years to arrive this asteroid. The arrival is 2031. So I do hope that spacecraft will not be broken. Before arriving this asteroid, we have one asteroid flyby, 2001 CC21 in 2026. And then we will have 2 Earth thingbys, and finally, spacecraft arrived to this asteroid. This is very interesting. The size is just 30 meters in diameter, and the spin period is about 10 minutes, very fast rotating. Such object has never been explored yet, so if we can arrive to this asteroid, I think we can know many new things. And this asteroid was observed last December by very large telescope like Subaru telescope of Japan or VLT or GTC. But you can see only small dot here. So I hope 10 years later, we can see this asteroid clearly. Okay, maybe the time is over. Like this, Hayabusa2 is a very challenging and exciting mission, and all the missions were successful. So now we have lots of samples. So I hope that we can understand Ryugu much more by using this sample. Okay, thank you very much for your kind attention.
Thank you so much, Professor Yoshikawa. It's really accuracy is the key for this very complicated mission. Really, we are talking about, it's not an easy to communicate and remote control of 300 million kilometers. It's around 50, twice the distance between the Earth and the Sun. 16 minutes light. Communication needs half an hour. Just send signal and receive it. Thank you so much for the accuracy. It's really a unique mission. I think right now, sir, we have Q&A, yeah? Yeah. Now, please, you can ask your question direct to Professor Yoshikawa, direct by writing text in the chat panel, or you can use the electronic hand and we'll choose it. Please. I think Dr. Ala al-Nahri. Dr. Ala al-Nahri from Vice President of Regional Center of Space Science in Jordan. Please, Dr. Ala, welcome. Dr. Ala, do you hear me? Okay. We have a question here from Jazz from Jordanian Astronomical Society. Jihad Sweden, please.
Dr. Ammar?
Yes, yes, please. Ask your question, please.
Good morning. Good morning. I would like to thank all parties that organized this seminar, Arab Union for Astronomy and Space Science, Japanese Embassy at Jordan, JAXA, Jordanian Astronomical Society, represented by its chairman, Dr. Auni Khassaouni, Vice President, Dr. Ammar Sakaji, for their great efforts preparing and organizing this seminar. And I would also like to thank Dr. Yoshikawa for his valuable information about Hayabusa2 mission. I have my congratulations to JAXA for this great and exceptional achievements in exploration the asteroid Ryugu by the probe Hayabusa2. Of course, I wish JAXA more success at the future. I have two questions, Dr. Ammar, to Dr. Yoshikawa.
Yes, please. Yeah, go ahead.
First question, did you start analyzing the sample that were brought from Ryugu asteroid by Hayabusa2, and when will the result expected to be announced and published? Second question, are there future plans to do similar mission to other asteroids, and what are the aspirations and the plans of JAXA for the next future stage? Thank you.
Okay, thank you very much for your kind words. Yes, for your first question, the analysis of sample will start June of this year. So I think the result will be announced at the end of this year or in the first half of next year. Okay.
Okay.
So yes, and as for your second question about the future missions of JAXA, and now we do not have asteroid sample return mission in future in JAXA, but we are discussing the sample return from Phobos. Phobos is the satellites, one of the satellites of Mars. We call MMX mission. So now we are working hardly to make a MMX mission. Is it okay?
Okay, thank you, Doctor.
Thank you. We have a question from Dr. Ala Al-Nahri, Vice President of Regional Center of Space Science in Jordan. Please welcome, sir.
Okay, thank you very much. First of all, I'd like to appreciate Professor Yoshikawa for his very, very nice lecture for us. I'd like to ask about something. Since Nozomi 1998, this failure mission, you didn't go, or you don't go to investigate Mars. As you know, Mars is very important planet to be studied. I don't know why. You tried with Germany and France to investigate Deimos and Phobos, the moons of Mars, but till now you didn't go, or you don't go to Mars. As you know, asteroid belt located between Jupiter and Mars. And I want to ask about another thing. Why you don't investigate the precious metal planets like Psyche 16, which has a very big amount of gold and platinum? I'd like to ask about those things. Why you don't go to Mars till now, and why you don't go to some wealthy asteroid in the asteroid belt between Jupiter and Mars?
Okay, thank you very much for your questions. The first question is why we didn't go to Mars after Nozomi. Yes, yes, this is a good question. And actually, the project team of Nozomi wanted to make another mission to Mars, but in Japan, we don't. The budget is rather limited. So next planetary mission was the Akatsuki, a Venus mission. So they couldn't try Mars again. But we, Hayabusa and Hayabusa2, we have a good heritage of sample collection. So using this heritage, using this technique, we chose another mission, another sample return mission from Phobos of Mars. Okay, so of course we want to do the Mars mission in future if we have chance.
And what's about
your second question?
Asteroid belt, wealthy asteroid belt or precious metal asteroid belt?
Yes.
You don't like gold?
I don't know whether such asteroid exists, but I am very interested in M-type asteroid, which may be metal, which are metal asteroid, M-type. So in Japan, some people discussed about the a mission to such a M-type asteroid, but still we don't have a mission proposal for M-type. Maybe I think this is very interesting object for the next target of Astro sample return. Yeah, you're right.
Okay, thank you very much.
Thank you.
Thank you, sir. I think we have another question from Professor Osama, Dr. Osama from Egypt, from University of Cairo and University of Beni Suef. Please, Dr. Osama, join us.
Hello.
Hello, yes, please.
Hello, everybody. Let me first of all thank Dr. Auni and his team for this very interesting event. I would like to appreciate also our colleagues, our Japanese colleagues, for their interesting Yoshikawa-san and highly excellent, the ambassador of Japan in Jordan. The point which I dream of is that to have a sustainability of such events. That's why I would like to not be the first, but the last, but to continue these events on bi-weekly or monthly, or even each 3 or 6 months, to get more bridging to the culture with the Japanese colleague and this scientific amazing work, I would like to say, in this event. Thanks again. And my questions to Yoshikawa-san about the absorption that you have seen for the water. This will be a good achievement to our scientific goal from the mission. Of course, the mission has a lot of interesting scientific outcomes on the technology, on the engineering, on science, as well as that exploration and the key of the origin of our solar system is beyond these asteroids emissions discovery. So I would like just to comment on that spectrum, because this might be the first indication of the water in the asteroids. Thank you again, and I wish you all the best. Regardless to also the exploration of the Mars moon focus, is that planned or not yet approved the mission? Thank you.
Thank you very much for your kind comments. As for the MMX Mars focus sample mission, it is almost approved. So
good.
Yes,
this is good news.
Yes, I think we can continue this.
The point I would like also to see that this great achievement has quite a number of institutes and collaboration. The management of this space mission really interesting and amazing for me, how to organize all this collaboration within Japan as a national, and also in the international collaboration. As far as I saw from your presentation, you contact with ESA, European Space Agency, and some other institutes from Germany to help in this or to cooperate in these missions. So how about the number of institutes? Can you give us an idea how many engineers, how many institutes, how many scientists go in these amazing missions? Thank you.
Yes. Okay. Yes, you are right. We have rather big team. And as for the science team, the number of members is about 300. for just the remote sensing science. And in this 300, more than 100 people are non-Japanese, foreigners for us. And as for the initial analysis, the science, the number of researchers is about 250. So in total, more than 500 people are working for the science of Hayabusa2. And I think the number of institutes is more than 20, maybe more than 20, 20 or 30 institutes, maybe. Actually, I don't know how many institutes, but there are many. I think more than about 30. And of course, we have many collaboration with other countries, like Germany and France, and the United States too. We have a very nice collaboration with USA. They support the navigation of spacecraft, and because Japan has a big antenna only inside Japan. So if we must communicate with spacecraft 24 hours, we must use the antenna in United States or Europe. So we have very nice collaboration with United States and ESA. And of course, we have good collaboration with Australia because the Capsule Reentry places Australia.
One more question, just please, if you don't mind. Regarding to the sample distribution, you will start from June, I think, this year, and then internationally distributed.
International distributed is June next year.
Okay. On what basis you are distributing this sample? Is that they propose projects before, or later you will announce for this?
Yes, I think we will make announcement in next year, and we will make a announcement of opportunity AO for the proposal. I think the AO will be done maybe spring or summer of next year, before summer. I mean before summer of next year, spring.
Great. So we wish to have an opportunity, if this is available, or to receive that AO, and then we can see how opportunities we can achieve that in our labs. Or
thank you.
Thank you again, YOSHIKAWA-san, and thanks also for all your team. You have a great team. I saw the pictures. It's wonderful young people that work with you. Congratulations. Congratulations.
Thank you very much.
Thank you. Thank you.
Before going, if you have now a question on the chat panel, we have a question from Astrogate about, can you just talk very brief about the propulsion system of that spacecraft which just arrived to the...
Can I ask the question?
Yeah,
because there are 3 questions, I can make them in one. First, thank you, Doctor, for your amazing presentation. I am Rami Imad from Astrogate Science Education YouTube channel. And we have questions from Tariq Saidi, Dr. Akram, and Ahmed Ibrahim Al-Askari. They are asking about, is there any new technology to reduce the time needed for to get and visit other asteroids, maybe using solar sails or other technologies? And regarding the xenon, why did you only use 50% of the xenon? Did you add more xenon than you thought you need? And regarding the power generation, why didn't this mission have a nuclear thermonuclear generator instead of solar panels like Voyager 1 and 2.
Oh, okay. So, sorry, the first question was what was the first question?
The first question was basically what other technologies you can use to reduce the time to get to asteroids?
Okay, I understand. So, yes. So in JAXA, we launched a small solar cell satellite. We call it Icarus, and it was successful. So after that, we planned to make a much large solar cell spacecraft, and we proposed it, but it was not accepted. Actually, we explore Trojan asteroid near Jupiter by using the solar cell spacecraft, but the proposal was not accepted. But maybe we will continue to study solar cell spacecraft from now on. And the next question is Xenon. Yes, after 6-year travel, we still have 50% of Xenon because we put a lot of Xenon in the spacecraft, because if we have some trouble, we need much Xenon. But we did not have trouble to go and to come back. So still we have 50%. So that's why we could choose another asteroid to go. And last question is not using the solar paddle, but something nuclear power. This is a good question, but in Japan, it is not easy to launch nuclear power thing. So we did not study this much. Okay.
Thank you. We have other question from UK, from Professor Suhan. Please join us.
Yeah, good morning, everyone. Thank you very much. Excellent lecture. Precision, wow, it's out of this world. And I think we can send something to the nearest Alpha Centauri system. But my question is pertaining to the asteroid itself. That, you know, space is full of water. Water is everywhere in space, but yet you don't see any ice on the surface. Why is that?
You mean we did not see ice on the surface of celestial bodies?
Yeah, that's right. You'd think that because there's a lot of water in space, you think that at least there will be some ice somewhere. You know, I'm surprised that actually it's barren.
Yes, but for example, the satellite of Jupiter and Saturn, the surface of such satellite is covered by ice. So ice is not. I mean, I think ice is common in the solar system, especially far from the sun.
So my second question is this lecture going to be available online?
Yes, sir.
Yeah, I'd like to see it again.
Okay.
Thank you very much.
Okay, thank you. We have a question right now from Oman, Dr. Saleh Shidani. Please join us, Dr. Saleh.
Thank you very much, Dr. Ammar. Really appreciate this opportunity to learn from this very rich and very fascinating experience from the JAXA, and we are very pleased that with their fascinating team, they managed to reach this highly valuable mission and with very accurate and very high precision. So congratulations for JAXA and for And many thanks, Professor Yoshikawa, for this very motivating presentation. I really love it so much, and I'm very pleased and very proud to see this achievement have been done by you and by the human, so they can explore further in the solar system and even beyond that. My question, and have you thought about the reusability concept? Now that you have achieved a major success with the Hayabusa 1 and 2, and I think now you are set to think along the reusability concept, where the spacecraft, after achieving this high precision and control and robotic and automated task, can it be used in multi-task, in multi-mission, especially when we consider in the near future there will be a base, lunar base, where this type of mission can be revisited the moon much easier, and then maybe refuel or maybe re-equip with a new probe or new equipment, so to give it, make it ready basically for the next mission. Have you thought along those lines?
Oh, thank you for your question. Sorry, I cannot catch your words clearly, but your question is, in future, JAXA will do some mission, not the asteroid, but the moon?
No. My question is the following. Since now you have a well-established technology that proven that you can use it and you can control the mission very successfully with high precision to go to all these asteroids and so forth, do you think you can slightly extend this concept to make it reusable? So instead of the mother spacecraft designed for one mission, it will be designed for multi-mission. So you send it to one asteroid, take the sample, bring it, and then after that, when it comes back, it is ready to be refueled or be integrated with a new probe, and then you resend it again. So basically, the concept here is to reduce the cost, since you managed to develop excellent technology now with this major success. I think it can be extended to make it reusable. So rather than focusing each time in the whole system, the whole spacecraft, you only focus in the new probe, the new addition to it that can be integrated. So it's a concept that I think it will lower the cost and will give more value, more benefit from your investment.
Oh,
I hope that's clear now.
Yes, I understand. Yes, yes. Actually, your idea is very excellent. However, reuse of spacecraft is rather difficult. For example, when spacecraft comes back to the Earth, the velocity is very high. So it is difficult to make a rendezvous for refueling. So maybe, yes, if we can do many sample returns by one spacecraft, it is very nice. But I think it is rather difficult. And at least up to now, it is easier to make separate spacecraft for each target.
Thank you, sir.
I just thought
that time is limited for Dr. Yoshikawa. Just we have, because I think he had to leave for a press conference right now after a few minutes. We have just 1 minute. 1 minute question. Rima Al-Akash from Jazz. Please quickly.
Thank you. First of all, I would like to thank you for this fruitful lecture. So I want to talk about these samples, which is carbon as asteroids, which should preserve the most pristine for material in the solar system. this mixture of mineral and ice and organic. So I want to ask this study, which extends to provide more knowledge, our origin evaluation of our inner plant. So as I heard and as I learned from the Google, so do you think this sample will help and useful to find a solution or any future proposal for us to solve the global warming, which is affected by the CO2? Recently, we heard about how they
I think there's a problem with your connection.
CO2 to a carbon as a slide material. So this is my.
We can't hear you. We can't hear you, Rima.
The second one.
Okay, I think there's a problem with communication with Rima. We are so sorry. Sorry, Rima. I think we have another question.
Hello?
Yes. Welcome, Dr. Yoshikawa, please. Have you got a question?
Now, it's okay?
Yeah. Please quickly, direct to the question, Rima. Hello? Hello? There's communication problem, I think so. No problem. I think now it's 12 sharp. Yeah. And thank you so much, Dr. Yoshikawa, for your time. And it's really amazing lecture and QAs. And it's a unique mission to this asteroid. I'm looking forward for next Japanese missions in 2029 and 2030. Thank you so much for your time. Thank you.
Thank you very much.
Thank you. Yeah, right now we continue our seminar on Dr. Hanna Sabat. Dr. Hanna Sabat?
Yes, I'm with you.
Yeah. Now Dr. Hanna Sabat will give us a presentation about the history and the orbital dynamics of Ryugu asteroid. Please, Dr. Hanna, he's from Jordanian Astronomical Society. Please join us. Welcome. Welcome, sir.
Thank you. I just need to share my screen.
Yes, please.
صوت واضح؟
Yes.
Okay, wonderful. Okay, good evening, everybody, and thank you for this interesting talk, Professor Yoshikawa. I have really enjoyed it, and I'm going to talk now about asteroid Ryugu from an orbital point of view. But before I start, I would like to check. Okay, good. Now, in order to identify or introduce this asteroid, its official name is Ryugu, or 162173 Ryugu, which means the Dragon Palace, as Professor Yoshikawa has earlier indicated. It has a provisional designation, which is 1999 JU3. It was discovered by Linear. We're going to talk about it briefly in a moment. And the discovery site was the Lincoln Labs ETS. And the discovery date was back in the 10th of May, on the 10th of May, 1999. Now, concerning Linear, the Lincoln Near Earth Asteroid Research, actually, it is a project which is a collaboration of the United States Air Force, NASA, and the MIT's Lincoln Lab for systematic detection and tracking of near-Earth objects. Lunar was responsible for the majority of asteroid discoveries from 1998 until it was overtaken later on by the Catalina Sky Survey in 2005. Of course, it's interesting to note here that this linear system has detected around 200,000 or 231,000 new small solar system bodies. Of course, some of which, around 2,400, were classified as near-Earth asteroids. Now, if you want to classify Ryugu from an orbital point of view, it's classified as a near-Earth object, or NEO. I'm going to explain this in a moment. And as a subclass, it's called a potentially hazardous asteroid, PHA. If it's an asteroid, we call it PHA. If it's an object in general, we call it PHO for object. And it is a part of the Apollo group. Now, what is an NEO? A near-Earth object, or NEO, is any small solar system body whose orbit brings it into proximity with Earth. Well, this is not a precise definition, general definition, but by convention, a solar system body is considered as an NEO, or a near-Earth object, if its closest approach to the Sun, which we call the perihelion, is less than 1.3 astronomical units. Just a reminder, of course, that the AU, or astronomical unit, is the mean distance between Earth and the Sun, which is around 150 million kilometers. Now, a potentially hazardous objects, PHO, which is also a class of near-Earth objects, is a near-Earth object that is either an asteroid or a comet with an orbit that can take it in close proximity to Earth, and which is large enough at the same time to cause significant damage in the event of impact. Of course, very small objects like normal asteroids are not considered as PHOs. Now, to be more precise, PHOs, or potentially hazardous objects, are defined as having a minimum orbital intersection distance with Earth of less than 5% of an astronomical unit, or around 20 times the lunar distances. That means any object, if they orbit, what we mean by the minimum orbital intersection distance, it's if we take the orbit of the Earth and the orbit of this object we are talking about, if at any point between the two orbits, the distance is around 20 lunar distances, then we consider it as PHO. And at the same time, it should have another condition, is to have an absolute magnitude of 22 or brighter. That means it's large enough. Now, to talk a little bit about the Apollo asteroids, they are a group of near-Earth asteroids named after the 1862 Apollo asteroid, which was discovered by German astronomer Karl Reinmuth in the 1930s. The Apollo asteroids are Earth-crossing asteroids, actually. They have an orbital semi-major axis greater than that of the Earth, that means greater than 1 AU, but their perihelion distances, the perihelion, which I'm going to talk about later on, is the minimum smallest distance in orbit, the orbit of an object, the closest approach to the Sun. So these objects have the perihelion distances less than the Earth's aphelion, which is about 1.017 AU. Now, in order to understand the orbital properties of any object in the solar system, I'm going to start from the basic principles. So what is an ellipse? An ellipse, it has certain geometrical properties. It is defined, if I want to use the official geometrical language, as the points that have a geometrical loci where any point with the geometrical loci where the distance from two fixed points, S and S prime, is constant. Or if I want to rephrase that, if I take any point and on this ellipse, let's say point P or P1, if I get the distance, the sum of the distance between P1 and P1S and P1S prime, Now, the sum of this distance is always a constant. Where if we take any other point like P2, P3, etc., the sum of distances PS plus PS prime is always a constant, and this constant is equal to 2a. 2a is the semi-major axis. I'm going to show you in a moment. So here we will define those two fixed points. We call them the focus, the foci. It's the plural of focus. And here, let's say that if we are talking about an orbit, S represents the focus and S prime the empty focus, which has no physical meaning, but only its geometrical or mathematical significance. O is the center of the ellipse, and the point A is considered as the perigee or perihelion. If we're talking about an orbit around the sun, we call it a perihelion. And point A prime, we call it the aphelion. Perihelion is the closest approach of this object to the sun, and the aphelion is the furthest point in orbit from the sun. Now here we define the semi-major axis as the distance between O, which is the center, and A, or O and A prime, it's the same thing. And we may also define the semi-minor axis as OB or OB prime. Now, the major axis itself is the distance between A and A prime, and the minor axis, the distance between B and B prime. Now, to any orbit or to any ellipse, we may define the eccentricity, which is defined simply as the distance between OS to OA, or OS prime to OA prime, or more generally, the distance between the foci, SS prime, divided by the major axis A prime. Now, in general, for an ellipse, the value of eccentricity lies between 0 to 1. It should be greater than 0 or less than 1. The bigger the figure, that means the more elongated the orbit is. Now, if E equals 0, the special case where E equals 0, we have a circle. That means S and S prime and O become 1 point, and we have a perfect circle. As E gets bigger, we are further away from the circle and more into the elliptical shape. For E greater equal to 1 or greater than 1, we have open orbits or open, parabola or hyperbola. But of course, I'm not going to talk about them in this lecture. Now we can also, I'm going to get a little bit more technical. We can estimate the distance of, I think there is a mistake here, sorry. This is the perigee, or perihelion, the closest approach. Here it should be RA equals A, which is the semi-major axis, times 1 minus E. And if we talk about the greatest distance, the apogee or aphelion, RA equals A, which is the semi-major axis, times 1 plus E. That means A and E are two important parameters in this context, where A is the semi-major axis, and A at the same time is the mean distance of the object in orbit between the object and the sun, if we are talking about the sun. So this is called, this is one of the orbital parameters, A actually, the mean distance or the semi-major axis. And E, of course, is the eccentricity is another orbital parameter in this regard. Now, one more thing we have to, of course, we can relate the semi-major axis with the semi-minor axis via this formula. I would like here also to define what we call the latest rectum. The latest rectum, now, how to understand this point? Now, this is, say this is the sun and this is the orbit, and we can erect a vertical line.
You have 7 minutes, please.
Okay, we can erect a vertical line on the semi-major axis. It intersects the ellipse by the points Q and Q prime. Now, this distance Q and Q prime may be defined as P equals A. The semi-lattice rectum, which is half the distance SQ. We call it P, which is A times 1 minus E squared. Now, of course, I'm not going to talk about the full two-body problem here. We don't have time. But a solution to the two-body problem in the classical mechanics, we get this formula, which gives you the distance of the object as a function of f. F, we call it the true anomaly. Now, the true anomaly, let's say this is the planet, and this is the direction of the planet. The angle between the between the perigee or perihelion and the planet is called f, the true anomaly. Now here we have another important point, which we call the first point of Aries. It has an angle omega. Now, just to give you a quick idea, these are some of the parameters, orbital parameters of the solar system objects. For example, here we have the distance in astronomical unit. In the case of the Earth, it's 1, and here in kilometers. And of course, the orbital period can be related to the orbital distance or the mean distance using Kepler's third law. And here you have the eccentricity. Sorry. Of course, they are very low, except for two objects which are highly elliptical, which are Mercury and Pluto. Of course, it's not a planet, but it's a solar system object. As was mentioned earlier, it's called a dwarf planet. Now, if we take a look at Ryugu's orbital properties, it has a semi-major axis of 1.189 AUs. That means on the average, it's further away than the Earth. Its perihelion, closest approach to the Sun, is 0.96 AUs, and its aphelion is 1.4 AU. It has an orbital period of 1.3 years. Now, this is just to show you how the eccentricity affects the shape. Now, if you have a complete circle, it's shown in red with E equals 0. In the green shows the eccentricity of 0.2, which is around the eccentricity of Ryugu. Now, there are actually 6 complete parameters that are needed to totally describe a body's or a planet's elliptical orbit, which we call orbital elements. Now, already I have talked about 2 of them, which is the mean distance or semi-major axis A and the eccentricity E. We have other parameters such as the orbital inclination I, the longitude of the ascending node of the orbital plane to the ecliptic omega, capital omega, the longitude of the perihelion, small omega, and the time of perihelion passage or the object longitude at a given epoch L. Of course, here we have to imagine, it needs a little bit of imagination. Now imagine that we have, this is the orbit of the Earth around the Sun. And of course, we have the projection. We may imagine the sky as a sort of globe surrounding the Earth. This is just a useful way to do it. And if we just project the orbit of the Earth on this globe or the sphere, the celestial sphere, we get this line, the red line, which is the celestial, we call the ecliptic, sorry. And if we project Earth's equator on this sphere, we get the celestial equator as well. Now there's an angle between the two. This is due to the inclination of the Earth's axial tilt, axis, that means of rotation, which is around 23.4 degrees. Now the points of intersection of these 2 circles, great circles, actually represent the vernal equinox and the autumnal equinox, which the vernal equinox, we call it the first point of Aries. It's a important reference point in astronomy, in coordinate systems. Now, if we erect the Earth once more, we can imagine this is the ecliptic. Actually, around this circle, there is an apparent motion of the Sun. It moves yearly around this circle and intersects the celestial equator by the 2 points, as I mentioned. So the vernal equinox is important, very important from the point of view of coordinate systems or celestial coordinate systems. Now, one more thing. This is the ecliptic, which is the plane of orbit of the Earth around the Sun, which we consider it as a reference point or reference level. And here we have an arbitrary object turning around or orbiting the Sun. Now, we have 2 important points here. It intersects the ecliptic by 2 points, while coming from beneath the ecliptic and above, we call it the ascending node. And later on, we have the descending node when it's passing from the above the ecliptic to below it. Now, this is an important line. We use. Why? Because we can define several things by this line of nodes. For example, we may define capital omega, which is the longitude of the ascending node. Of course, with reference to what? To gamma. Gamma here is the first point of Aries, or the vernal equinox I referred to earlier. And we have also omega, which is the argument of perihelion. So, and the I is simply the inclination. We take a vertical line, that is a line perpendicular to the orbit of this object, and another one vertical to the ecliptic. And the I is just the angle between these two vertical lines, which is the inclination of the orbit. So this is basically, these are basically the orbital parameters we are talking about. Here you have a few orbital parameters of the solar system objects. Of course, most of them are small, but for example, the case of Mercury, it's around 7. And I think Pluto has the record, which is 17 degrees. When I talk about large objects, it has a 17-degree inclination. Now, this is finally, before I finish, I just want to talk about some of the methods we use to determine these orbital parameters. We will define the mean angular velocity, or the mean motion, as the complete circle, which is 2 pi divided by capital T, or P, which is the orbital period. So n equals 2 pi divided by T. And here we may define what we call the mean anomaly. Now, the mean anomaly cannot be represented graphically. It's simply the mean value, or the mean motion, divided by the time of the perihelion passage. Now, if you consider this ellipse, and if we erect an eccentric circle around it, we may define an eccentric circle as well. This is important to solve to find the relationship between time and f, which is the true anomaly, or this angle. Now, without going into too much detail, we finally get to what we call the Kepler's equation, which says that E, this eccentric angle E, capital E, minus E, which is the eccentricity, sine E, equals m, which we calculated earlier. And this equation might be solved numerically or by iterative methods. So finally, to sum up, if we start with the A, the semi-major axis, and the mean, or the mean distance, and the eccentricity, we may estimate the B, which is the semi-minor axis. From A, and using Kepler's laws, we may get the orbital period, T. Here we have the mean motion, 2 pi over T. And by putting it into this equation, we estimate the mean motion, the mean anomaly. And finally, solving Kepler's equation, we may get E, the eccentric anomaly, by putting the value of E, eccentric anomaly, with all the other known parameters, which is the eccentricity. We get F, the true anomaly, which is, I remind you, is the angle between the aphelion and the position of the object we are talking about. And then, using this equation, we can get the distance of this object. And if we want to estimate its velocity, we may use what we call the vis-viva equation. So basically, this is the scheme usually used when we want to estimate the position and velocity. And of course, we may translate this into position as well. Now, if we get back to Ryugu, we have already talked about some of its orbital characteristics. And now we have the mean anomaly for this object, which is around 3.98 degrees. This is its mean motion. The inclination is around 5.88 degrees. This is the longitude of the ascending node, 251 degrees, and the argument of perihelion, 211 degrees. Of course, these values may change. One thing we'll have to bear in mind, we are not talking about purely two-body problem, because we have perturbations. That's why these values, we call them the oscillating orbital elements. But actually, we have always to renew them to take into consideration the effects of perturbations from other planets and other factors which perturb the values of these 6 parameters, which makes them change with respect to time. Of course, for smaller objects in the solar system, these parameters change rapidly, but for larger objects such as Jupiter, Saturn, they are much more sensitive to perturbation, much less sensitive to perturbations. Now, this is just to show you, this is based on some old information, actually in 2015 and 2016. This is Earth's orbit in blue, and this is Ryugu's orbit in green. And thank you for your listening.
Thank you so much, Dr. Hanna, about the orbital dynamics of Ryugu asteroid. Thank you so much.
You're welcome.
Would you please share your screen?
Yes, sure.
I think it's my presentation now.
Yes.
My screen is okay?
Yes.
Thank you. I would like to talk about the orbital dynamics of the asteroids 2001 AV43 and 1998 KY26. The first one is, I think, extended Japanese mission in 2029, and the second one in 2031. So we'll talk about right now very quick about the orbital dynamics. Asteroid in general is a rocky metallic bodies that orbits around the sun, and the composition is nickel and iron. And they are the source of the asteroid comes from the asteroid belt. And distances between the asteroids, there's millions of asteroids in our solar system. And as a first estimation, 1.1 up to 1.9 million asteroids larger than 1 kilometers in diameter, and millions of small asteroids. And near-Earth asteroid, I think, discussed by my colleague, Dr. Hanna. And this is distinguished between asteroid, this is a big object, and this meteoroid is a fraction. It's part of when there's a collision between asteroids, there's a small fraction called meteoroid. If it's land on the Earth or around the Earth, we call it meteoroids. This is the asteroid belt around the sun. And this is also, our solar system, this is the sun, and this is the Earth, rotates around the sun, and this is Mars. And this is the asteroid belt, and this is called Apollo near Earth object, which is, I think, very important for our discussion today. Asteroid mining is the exploration of the raw material from asteroids and other minor planets, including near Earth object. Orbital elements, I think, discussed by my colleagues. I will skip it. Yeah. Now, as we discussed, we have two extended missions. The first one will be 2029. It will be in the asteroid 2001 AV43, and the second one will be in 2031 about the asteroid 1998 KY26. And this is the orbital mechanics, and this is also the, I think it's very important to understand. This is the sun, and this is the Earth rotates around the sun, and we can transportation and mining missions. And this is the Earth, this is the satellite, and how the satellite arrived to asteroid and back to the Earth, as discussed by Professor YOSHIKAWA. Now let's back to try to understand and what is the asteroid 2001 AV43. It's classified as near Earth object and first observed by Lincoln Laboratory, New Mexico, 2001. It's very small, and this is called fast rotator. Fast rotator means it rotates around itself, and I think and it's very small asteroid, around 30 meters in diameter, and the shape of that asteroid looks like S-shaped asteroid, and the period, this is why we call it fast rotator. The period of rotation around itself is around 10 minutes. We are talking about 10 minutes period, 10 minutes spin around itself. And it's right now in the Iris constellation. This is the position right now of the asteroid AV43. This is the sun, and this is the Earth, and this is its position right now in this graph. Now, I collected a lot of data from GPL and about the close approach date. Why the Japanese mission choose 2029 for that mission. There's a big data called close approach data, and from 1914 up 2124. This is from NASA JPL laboratory. I just collected the very close. I call this data very close approach. Look here, in 1973, this is distance between us and that asteroid, AV43. It's around 0.00 AU, 0.0039 AU. AU means the astronomical unit. It's the distance between Earth and Sun. It's around 150 million kilometers. And the closest one, look here, it is 2029. It's around 0.016, very close. Look to the chart, right hand. I sketched these numbers here. This is the period why they choose that time for AV43 mission, because at that time it's very close to Earth, very close to Earth. This is why we'll choose it. This is discussed. This is some research papers about the calculation of gravity on that satellite, and this is published. That the first data published by a journal by Whitney 2002, and this is the asteroid 2001 AV43, and this is the period and all the elements here. Now, can we see that asteroid? It's very difficult. I think it's right now in Amman. It's above the horizon. It's a magnitude around 27, which is very difficult. We need a larger telescope around 8.5 meters and above. But maybe there's some techniques called long exposure photography techniques that takes advantage of slow shutter speed to create a creative, unique-looking imagery. Maybe we can see it. It's right now, if you want, rise and set time of that asteroid in Amman right now will be, I think, this round. It's more azimuth is 77, maximum altitude is 71, and rise is 7:43 morning, transit 14, set 20. So it's difficult to see it because and we have to wait before sunset around this time, but we need larger telescope to see that asteroid. And orbital elements discussed by my colleagues, Dr. Hanna. I will not talk about more technical details about this asteroid. And this is also an important chart about distance of that asteroid from 2020 up to 2026. And this is in AU units. This is distances. We can see it in the chart. And this is the magnitude. It is around right now, these days, it's 27 magnitude, and it's fluctuated. It started from this chart around 27 and up and down, but it's around 27, 24, 25, which is difficult to observe from the Earth unless we have a larger telescope. And this is the telescope diameter as a function of limiting magnitude. For apparent magnitude 27, I think visible light limits to 8-meter telescope, and there's some in Japan, in Chile, there's some 8-meter telescope. We can use it to watch that asteroid from the Earth if there's a very good condition for observing. This is a very short overview about this asteroid. Thank you so much. Right now we come to the last session. I think Dr. Mr. Adli Halabi. Adli from Jordanian Astronomical Society. He'll talk about 2021 space missions. Please join us.
Okay, Mr. Ammar, Dr. Ammar, how are you? Thank you very much for your presentation. And I would like, before I review my presentation, I would like to thank the distinguished, valuable participation from JAXA, Professor YOSHIKAWA, and Japanese Embassy in Jordan. I will start my screen now, sharing to my screen. It is shared now. Dr. Ammar, it is shared now. Hello, Dr. Ammar.
Yes, sir. Yes, it's okay. Go ahead.
It is shared already?
Yes.
Okay, thank you very much. I will start for my review for upcoming space missions or the remaining space missions in this year and for the near future nearby missions. We'll start with the James Webb Telescope. After many technical delaying for this launching this James Webb Telescope, it will be finally planned to be launched in the end of October. By the way, this telescope, it is 100 times more powerful than the Hubble Space Telescope and optimized for infrared wavelengths. Of course, will be targeted the first galaxies that form the early universe, and hopefully will be succeed in launching this time. The other missions it will be launched for the Chinese space station. It planned to be launched the core model. The core model name is Tianhe during this year, and later on in the next year we're launching the experiment module of Wentian and Mingtian, were planned to be launched in the 2022. Another missions, it is now targeted to be launched this year, during this year. It is a pre-green lander, and this lander will take the first batch of the 28 Ellipse payload to the moon in June, including 14s from NASA. If all goes well, it will be the first private spacecraft to successfully land on the moon. Intensive machines will launch a Nova C cylinder to the moon in October aboard SpaceX Falcon 9 rocket. It will be take at least 5 NASA payloads to the moon. This is a private project and primary projects for Artemis program. Another missions, it will be launched this year or May on in November. The Artemis 1, the mission will test out the Orion vehicle hardware, software, and life support system. Of course, this is a part of the government human space flight program that has the goal to landing the first woman and the next man on the moon. Another missions, it's the Martian's Moon Explorations, MMX, is a robotic space probe set for launch in 2024 to bring back the first samples from Mars' largest moon, Phobos. Phobos, by the way, it's around in diameter about 22 kilometers. The mission, whether the Martian's moon are captured asteroids or the result of the large body hitting Mars. By the way, this operation will be operated from JAXA and with international cooperation from NASA and ESA. There's another missions also. Smart lander for investigations moon Slim. Also, this is a JAXA mission. This is a JAXA missions and will be operated in the next year, in the upcoming years. And this is the first lunar surface mission. It will be determined the precise pinpoint lunar landing. Slim is planned to be launched together with the X-ray imaging and spectroscopy mission space telescope. Of course, the mission objectives will be the demonstration the accurate lunar landing techniques and acceleration, the study of the moon and other planets using the lighter exploration systems, and planned to the land near the Marius Hills Hole. It's a lunar lava tube entrance discovered by Kaguga. Launch date planned 2020 after 1 year. Kaguya, by the way, it's also a JAXA mission were operated in 2007. Okay, if there is another missions also, Destiny. It's a standby, a demonstration and experiment of space technology for interplanetary voyage with the Python flyby and dust science. It's a planned mission to fly by the meteor shower parent body 3200 Python, as well as the various minor bodies originating from the rock comment. And this mission is operated from JAXA with international cooperation from DLR, dust analyzer, and other operations missions. There's another interesting missions also from JAXA. It is Kunos. It's a standby oversized kit craft for exploration and astronautics in the outer solar system. Mission objectives to analyze the composition of the Jupiter Trojans may help scientists to understand how solar system was formed. The primary specification for this mission, main orbiter and lander, and the plan to complete a 12 years journey to 7 different asteroids and possibly return Trojan asteroid samples to the Earth in the 2050s. This is a cooperation between JAXA and NASA. Finally, the final mission, Lightbird, it is CMP-B mode polarization mission. Studies of P-mode polarization signals of cosmic microwave background radiation to detect evidence of primordial gravitation waves. And this this mission operated from JAXA, will be operated from JAXA. And this is the plan to launching in 2027. This is a quick review about the nearest upcoming missions 2021. And thank you, Dr. Ammar.
Yes, please. Thank you. Please, and share your screen, Adli.
Yeah, this is a quick presentation review for because we have a limited time. Okay.
Okay.
Now I've stopped sharing now.
Thank you so much. Now we have just 5 to 10 minutes for Q&A. Please, if you have question, use the electronic signal, or you can write your question in the chat panel, please. Please, if you have a question.
Okay, Dr. Ammar, I have a question. Dr. Ammar, I have a question for you. Okay.
Please, yes, go ahead.
If there is no raise handed for a question,
no,
I would
go ahead.
to ask this question. Do you think it is possible in the future to launching a mission, I mean from JAXA, since they have a very good experience in collecting samplings from asteroids, and it may be also from the comets? I think it is possible to launching for the interstellar objects, like MEMO. If you remember, this is before.
Yeah, I think that one is difficult a little bit. It's difficult. Yeah. I don't know. I'm not sure, but with enough technology, we can do it. And according to history, you have it. Yeah. I think Professor Ala Nahri has another question. Please, تفضل دكتور please, Dr. Ala. Please, sound. I can't hear you. Dr. Ala, check your mic, please. We can't hear you. I think there's a problem with the communication with Dr. Ala Nahri. Please. You are co-host. You have the privilege to close and open your mic, please, sir. We can't hear. Switch the mic off and on. Maybe that would help. Okay, we'll come back to you. We'll come back. Do we have another question, please? Or if you have any notes before closing? Professor Shawqi, do you hear me?
أسمعك.
Yes, please. If you have any notes or whatever, go ahead.
أنا في الواقع مستمع، وأنا أشكر كل المنظمين على هاي الندوة. وبالفعل اليوم اطلعنا على تكنولوجيا ما كنا نعرفها سابقا. يعني الكلام اللي قاله زميلنا من جاكسا يعني كان كلام مثل ساينس فيكشن.
Yes, it's a unique mission. يعني تخيل عم تعمل landing on a fast rotator. The period, rotation period is around 10 minutes. 10 minutes back and bring rocks sample to the Earth. It's amazing, really. It's amazing. It's very complicated mission, really.
It's very complicated.
بصراحة دكتور شوقي.
Let's talk in English, Dr. Ali Adli.
Okay, thank you. Actually, Dr. Shawqi, Japanese have a long experience in launching space missions to the asteroids. They have a back experience from the early 1980s. They started with comet, with Halley comet. They're launching a vehicles, space missions for Halley comet to collecting the dust. Analyzing from the Halley comet and then
أنا كنت أتابعهم من زمان، وكل هاي الكلام اللي ذكرته عفوا أنا ذاكره في الموسوعة اللي عندي. كل الميشنز مال اليابانيين من الأيتيز كنت أتابعها، خاصة هايابوزا 1 أنا كنت أحلم في الليل وأنا أسمع عنها.
by the way, Hayabusa 1. They use the same techniques and they of course upgrade the technical data and instruments by Hayabusa 2, but they take the same body. I mean the same main instruments. They use it for Hayabusa 1. They use it also for Hayabusa 2 because they have a background, big experience about the first missions of Hayabusa 1 to Ichikawa Asteroids.
الشيء الوحيد هو الفرق بينه وبين الميشنز الأخرى. يعني احنا نقارنه بميشن مع روزيتا الفرق بينها وبين هذه. روزيتا كان عنده مايكروسكوب علشان يشوفوا إذا كان في أي أشياء في الكوميت. هذول يعني يمكن بنهاية النقطة الوحيدة اللي ما فكروا فيها وما يحتاجوها. هو في الواقع ما تحتاج أنت مايكروسكوب، ما دام راح ترجع بعينة you don't need a microscope. فالعمليه يعني كلها معقده في غايه التعقيد. بس هاي هايابوزا 2 الفرق بينها وبين هايابوزا 1 شيء كبير جدا. يعني انت شايف كميه الاجهزه اللي استخدموها وكميه التحاليل اللي عملوها. وهبطت ونزلت 7 stages. ايه يعني هبطت ونزلت عده مرات. يعني مثل هايابوزا 1 مره واحده بهالشكل بالصدفه. ايه بس هذه كانت well organized. Very precise.
Yes, exactly.
I would like to take the opportunity to thank you for this opportunity to host such privileged. I hear myself. I hear an echo. I'm sorry.
There's some echo with your sound.
Okay, there is echo. If you can remove. Okay. If you can remove if someone playing the channel in Arabic, I'm sorry. Okay, thank you so much. I want to thank you for this opportunity to host such honorable guests, and I would like to ask if there are any planned collaboration between JAXA and any of the Arab initiatives or Arab space agencies in Jordan, in the UAE, in the KSA, in Egypt. I would like to know about that.
لا تقول أي شيء لما تفرجيني إياه.
اذا كان هناك اي مخططات للتعاون لاطلاق مهمات عربيه فضائيه بالتعاون مع جاكسا او غيرها من
in very brief, and there is some scientific collaborations and agreement between JAXA and the Regional Center of Space Science in Amman. There's some agreements, and we are going to have some scientific collaboration on that direction. Okay. Dr. Ala Al-Nahri, are you okay? Maybe still you have problem. Anyway, any question? I think everything is fine right now. We are arrived to the closing session. Closing session, I think Dr. Aouni, please. The President of Jordanian Astronomical Society, Dr. Aouni, do you hear me? Anyway, thank you so much. Thank you, everybody. Thank you for joining with us. And we thanks JAXA. We thanks the Japanese Embassy in Amman and Awas, Jazz. Thank you, everybody. And we thank Professor Yoshikawa again and again for your time. Thank you so much. He's hearing us. He's with us right now. He just finished his conference of press. But thank you so much. And looking for more detailed scientific collaboration between Jordan and Japan. And we have people very interested in orbital dynamics and calculations. Maybe in other seminar we can go more deep on solving Kepler's equation, especially when the eccentricity about 0.24 for the second mission K43. And how about to calculate when we have small anomaly? We have to add more terms of solving Kepler equations and add more perturbation. Maybe this will be a title of a seminar, how to calculate these orbits in more precise things. Professor Yoshikawa, if you want to talk about the mic with you, please.
Yes. So thank you very much for this seminar. Actually, I myself enjoyed this seminar very much. And it was my pleasure that I can talk with you. Thank you very much.
Thank you so much. Thank you so much. And looking forward more scientific collaboration. Thank you, and see you again for next seminars from Jordanian Astronomical Society and ours. Thank you.
Amar,
yes.
Can I just make an announcement about the NOCEL?
Yeah, okay, about your seminar, no problem.
Yeah, thank you. Good afternoon, everyone. My name is Sohan Jita. I'm from the network of researchers on the chemical evolution of life. On week on Saturday, that is 29th, 30th, and 31st March, in the UK and online, we're actually holding a seminar on the origin of life, which is how did it all begin. We have over 95 very good abstracts, and 95% of 48 abstracts, which are really, really absolutely brilliant. And you can register. Well, I can't give. Well, I'll put my email on the here, but you can contact either myself or ask Professor Amar how to get in touch, and you can actually sign up for it, and you won't be disappointed. Trust me, it would be as exhilarating as this has been organized by Professor Amar here. So this is my email.
You can write your email in the chat panel, please.
What's that?
You can just write your chat. You can write your email on the chat.
Right, okay.
Just write it. No problem. In the end, right now, thank you, everybody, and looking for next seminars. Thank you, everybody. Bye-bye.
Bye. Thanks.
Thank you.